Good afternoon, anyway, for all participants, students, lecturers, partners, and of course, our distinguished guest, Professor Byoung-Kwan from Chungnam National University, South Korea. Welcome to the guest lecture meeting today. We are very grateful to have a respected researcher who are happy to provide a lecture with the topic of imaging technology and hyperspectral imaging, principles, applications, current technologies, and challenges. First of all, let me read the curriculum vitae of our guest. Okay, Professor Cho is a professor at Department of Biosystems Machinery Engineering in Chungnam National University in South Korea, and he also a leader for non-destructive biosensing group, which work in the area of non-destructive measurement for quality and safety of food and agriculture materials. Next. Professor Cho finished his study in doctoral in agriculture and biological engineering from Pennsylvania State University in United States, and previously, before he finished his master's from Seoul National University and finished his bachelor from Seoul National University, South Korea. He is now acting as an editor-in-chief of Journal of Biosystem Engineering. He author and co-authors of more than 150 peer-reviewed journals, articles, and I believe still going, and 5 book chapters and maybe more. And he received more than 10 patent registration. He received some awards such as an Excellence Research Award from Chungnam National University in 2020, Excellence Research Award from Chungnam also in 2019, and he is now an editor. I have mentioned that. So next. His research area, he's interested in research about machine vision and hyperspectral imaging for foods and agriculture materials, spectral analysis and chemometrics for quality and safety measurement of biochemical materials, phenomics, abiotic, biotic stress monitoring technology for plants and animals, smart farm sensing technology, artificial intelligence, machine learning, deep learning for image analysis, and also for biosensor for food safety. Yeah, I think that's it. The story about Professor Cho. Now let's get started by greeting our guests. Good afternoon, Prof. Cho. How are you?
Hi, thank you, Dr. FP, for the introduction. It's my great pleasure to meet all of you through this special lecture. Okay, so can I start now?
Yeah.
Right.
Yeah,
okay,
I think you can start now. We have more than 100 participants.
Okay.
Not only from Gajah Mada, but also from various universities.
Oh,
or
maybe
some of your students are here too. And
all right.
today,
Let me share my slide then.
Okay.
Okay, can you see my slide now?
Yeah, it's clear. Okay, you can start now.
That's very good. All right. Okay, my name is Byoung-Kwan, professor of Chungnam National University in South Korea. It's my great pleasure to meet all of you through this lecture. Today, I want to talk about imaging spectroscopy and hyperspectral imaging. Actually, imaging spectroscopy and hyperspectral imaging is the same meaning. Imaging plus spectral information, also spectral and imaging combination. All right. Okay. My place is in Daejeon, South Korea, the central area of South Korea. There is, the capital city, Seoul, and my city is Daejeon. Daejeon means big field. So it is about 150 kilometers from Seoul. So 1.5 hours by car. Okay, Chungnam National University is in Daejeon City. And, the university is established in 1952, and we have about 1,000 professors and 18,000 undergraduate students and 5,000, graduate students. My research area, as Dr. Epi, introduced, I'm working on image processing and spectral analysis, automation, real-time sensing for agricultural materials and food inspection. Detail, I'm working with seed, fruits, and vegetables, also inside quality of fruits and vegetables, and online inspection for livestock and dairy products, and plant measurement and smart farm technology development. Also, fake food detection technology and chemical imaging for cooked foods and food safety with biosensors. Okay, this is a brief introduction about me, and let's move on the lecture. So why we need a system for sensing? System means, imaging device or machines. Why we need a system? Let's think about, these figures. Left figures, the color of A, the background color of A and background color of B. How do you think? The color is different or, same? Yes, it looks different, right? The color of A and color of B may be different, but let me cut and paste the color of A, okay, like this. Again, I will do it again, okay? Color A and color B. Actually, the color is exactly the same, but it looks different because of shadow, okay? Okay, let's think about right hand side figures. There are red color, red background. So upside red and downside red. How do you think the color is same or different? It looks different, but let's compare. Okay, the upside red and downside red is exactly same, but it looks different. So why the color looks different? Because our naked eyes is distorted. It influenced by circumstances. Some conditions. Okay, so our eyes is very sensitive for classification, but it's not good for measurement. Quantitative, especially quantitative analysis, our eyes is not good. So we cannot identify, we cannot quantify something with our naked eyes. So that's why we need system or machine or, imaging device for sensing, to detect something accurately. Okay, let's take a look, this video clip. This is cherry tomato sorting machines. Do you know how to, sort, the cherry tomato? What kind of system, what kind of, imaging device we are using now? Yes, the color camera, right? So we sort the tomato ripeness with the color. So the only, we need, devices, the only device is color, device, color camera, okay? So the ripe tomato is red and the unripe tomato is, green. So using that system, we can, sort the ripe tomato like this one. All right, then what is color image then? Color image consists of 3 wavebands: red, green, and blue. Okay, so using red, green, and blue color, blue wavebands, we can consist in a whole color image like this way. Okay, then what is color then? The color is a certain range of electromagnetic fields like this one here. Okay, let's see. There is a visible range here, right? Okay, visible means color because visible range we can see, but above the visible range, longer wavelengths is infrared, and the shorter wavelengths ultraviolet UV. Okay, the shorter wavelengths X-ray, much shorter, gamma rays, high power but very short wavelengths, and longer wavelengths infrared, radar, microwave, radio wave. Okay, but color image, color range is a very narrow range of electromagnetic field. In agriculture area, visible is very important, right? Many physical and some chemical information in color, but infrared image is also important because infrared, range has chemical information of material. So in agricultural field, visible and infrared is very important and widely used electromagnetic field range. Okay, let's think about infrared spectrum then. This is an example of molecular, campaign molecular. So every molecular vibrate always. Okay, vibrate always. So let me. It is okay. It is stopped, but okay. This vibration correspond this observation, and this vibration, this observation, this vibration correspond to this observation, because the molecule vibrate when light comes in. The light is electromagnetic field. Okay, the light has wavelengths. The inverse of wavelengths is frequency, right? So frequency means how fast it vibrate and how slow it vibrate, right? So there is a certain vibration. There is, they have frequencies. So if the light frequency and the molecular vibration frequency matches, the energy absorption occur. Okay, that's why the spectrum, the absorption peaks happens. Light frequency and molecular frequency is matched. There become energy absorption. So when we look at the spectrum, we can predict what kind of chemical composition of materials. We can predict it. So that's why we call infrared spectra or infrared spectrum as a fingerprint of chemicals. Okay, let's use spectrum for agricultural material. This is about the potato. Okay, sound potato and impacted potato is bacteria impacted potato. The outside it looks okay, but inside there are some bacteria infections, so it is bad. Okay. Okay, so let's illuminate. Let's illuminate the potato. Okay, so light comes in and then penetrate through the potato, and then transmitted light comes out. We can collect the transmitted light using spectrometer, and transmitted spectrum is like this way. Okay, the spectrum of sound potato and the spectrum of impacted potato is different or same? must be different, right? Because the chemical composition of, sound potato and impacted area, yeah, definitely this different. So that's why the transmitted spectra becomes different, from this, the sound potato from impacted potato. Okay, so using this principle, we make online potato sorting machines like this way. Okay, the sound potato, impacted potato, the spectrums becomes different, right? So using that information, we can make a prediction. I mean, classification model to discriminate infect potato from sound potato. This is blind test. So we just dump impacted potato and sound potato together and feeding automatically and moved to sensing area like this one. It's each individual cups. So light illuminated, light penetrated, and then the transmitted spectra is measured. So using the classification model, we can sort sound potato and impacted potato like this way. Okay. Yeah, we checked the accuracy. The accuracy is pretty good. Okay, like this way. Okay. Okay, let's think about another things. I introduce color imaging and the spectral measurement. What is the best then? What is the best technology? What is the best techniques for agriculture field? We don't know. Actually, I don't know, because it depends on material. It depends on condition. It depends on purpose. Okay. Let's think about this photo. Let's see this photo. This is color image, RGB image. There is a hidden frog. Do you know where is frog here? Very difficult to find the frog. Let's see infrared image. Can you see the hidden frog? Still, we cannot find that frog. Okay, NIR image. Still we don't know. But let's see. The thermal image is kind of tricky, but there is a small, spot, a red spot here. There is a hidden frog here. So my point is, in this case, the thermal imaging was the best technique for these special cases. So likewise, there is no best, techniques. There is no best technology. It depends on your condition and your materials. Okay. Okay, let's think about hyperspectral imaging. So why we need hyperspectral imaging? Okay, hyperspectral imaging is image plus spectrum. Okay, I guess two technology combination is better than just a single technology, maybe, because we can do more things compared to single technology. Okay, so image plus spectrum, then it can be used as a general techniques for agricultural sensing. Okay, that's the one advantage of hyperspectral imaging. Okay, then what is hyperspectral image? Okay, this is a color image. As I told you, the color images consist of 3 wavebands: red, green, and blue. Using these 3 bands, we can make color image like this one. But hyperspectral images has lots of wavebands, not just 3 wavebands, but it has 100 or 1,000 wavebands like this one. Okay, so the image the hyperspectral image, each pixel is like a spectrum. So you remember the spectrum has chemical information of materials, right? So hyperspectral image has image plus chemical information. Okay, that is the advantage of hyperspectral image. Okay, so image and each pixel is a spectrum. It has chemical information. So hyperspectral image has good advantages to measure physical and chemical information of samples. Okay, today I want to introduce three kinds of hyperspectral image technology. First one is hyperspectral reflectance image. So you know reflectance, right? Light comes in and bounce back. So if we measure the bounce back, a light intensity, it is reflectance. So likewise, hyperspectral reflectance imaging is the reflectance image measurement. Another technology is hyperspectral fluorescence imaging. Fluorescence, what is fluorescence? When light energy comes in, the atom, the electron is observed the energy and excited, and in a short time, it releases the energy because it wanna come back to the original state, and during the returning process, it emit the energy again. Okay, that is fluorescence emission. But fluorescence emission, the wavelength is longer than excited wavelengths because the power is lower than excited energy. So excited energy and then emission energy. So emission part, this is fluorescence emission. Okay, so we can use hyperspectral fluorescence imaging also because there are many fluorescence sensitive chemicals in agricultural materials. Okay, another technology is hyperspectral Raman image. It uses Raman scattering. Okay, what is Raman? I don't want to go deeper inside, but just I'm trying to I'm trying to explain very briefly. So Raman scattering. So we illuminate a material with a very strong light, like a laser. Laser is a high power, right? So if we use laser, there will be a scattering. Then near the laser wavelengths, it make very small peaks. Okay, this is Raman scattering peaks. Okay, so if we use this Raman scattering peak, we can identify the chemical structures. Okay, so hyperspectral Raman imaging is using Raman scattering. So okay, first let's move to hyperspectral reflectance imaging. This is an example of reflectance imaging. Pair bruise detection. This one is Korean pear. It's quite big and very sweet, and the texture is very crunchy. So it is a very popular, fruits in Korea, especially in autumn season. So let's see this photo. This is a pear. Do you think it's good or bad? How do you think? Is it good or bad?
Good.
At the glance, I think it's okay, right? It's good. But after peeling the skin, there is a bruise area. With naked eyes, it's very difficult to identify because the bruise areas is the beneath the skin. So if we peel the skin, there is a bruise area like this one. So this bruise area accelerate the return of pear. So we have to sort out this bruise, the pear. Okay, how can we do that? Because color image is not quite possible because the surface area is okay, it's no problem, but inside problem, right? So that's how can we do that? So let's use hyperspectral near infrared images. It's a reflectance imagings. The images at a certain wavelengths here. We could see some, bruise area here, right? Okay, and there is a, shiny spot. I mean, the hole is quite shiny. This hole is a renticer, which, exchange the air, I mean, gas. So anyhow, our target is bruise area. So we try to, think about, the chemical, I mean, spectral information of bruise area, and also it's a sound area. Okay, this is a spectral, information. How can we discriminate? How can we, classify these two groups? Okay, maybe we can use ANOVA test, or this is very simple, statistical analysis. There are other complicated analysis also, but let's use a very simple, analysis with the two wavebands. Let's select two wavebands and then one waveband and two second wavebands, just a division. Okay, so using this simple model, let's see, we can select in two important wavebands like this one, 1074 nanometer and 1016 nanometer division. We could identify, the bruise area clearly. Okay, this is a very simple detection algorithm. Okay, so with this simple detection algorithm, we apply that developed algorithm to the, pair. Okay, before bruising, everything looks fine. There is no symptom, but after bruise, we can identify the bruise area like this one, but the bruise area becomes bigger and bigger with the time. Okay, so with the time, the bruise area becomes bigger and bigger. Okay, so using hyperspectral reflectance imaging, we could monitor the bruise area non-destructively. Okay, I have to mention about the spectral analysis, briefly. I don't want to, go deeper inside because spectral analysis is very huge area. So if you go to, master degree or a PhD degree program, then you may learn spectral analysis. But I want to, introduce spectral analysis very briefly. Once we got, hyperspectral image, it's all about, spectral information. Okay, so the raw data is a spectrum. Okay, using that raw data, using that spectrum, we have to minimize the noise, unwanted, information, and then we have to extract some good information. Okay, that is a modeling. Okay, noise reduction is pre-treatment, I mean pre-processing. Okay, so using chemometrics. Chemometrics is modeling, kinds of modeling. So pre-processing, so reduction, noise reduction. So we need pre-processing and modeling. Okay. Oh, let's think about, this is an example. This is a spectra of a certain area. Okay. This is the same area, but let's look, this spectrum is quite, high variation. Even it's the same property, I mean, same, area is quite, different because of, agricultural material, sometimes a round shape. So the light, reflectance may be, different. Sometimes temperature is different. So it makes variation. Even the chemical composition is the same, but it looks different, spectral, intensity is different. Then how can we, reduce this variation? So that is about, pre-processing. So the question is, does this data look satisfactory to be used for further processing? Maybe or maybe not. Okay, so the data need to be cleaned prior to further operations. Okay, so that's the pre-processing. We have to minimize unwanted variation or unwanted noise. So using, this is just an example. There are many other pre-processing methods, but this is an example. So standard normal variate. This is a very simple equation. So S means standard deviation of a spectrum, and X bar is average spectrum. Okay, X is raw data. So using simple equation, we can minimize, we can reduce the scattering, scattering variation like this one. Okay, so we can reduce unwanted variation, or we can reduce the unwanted noise using pre-processing method. Now it's ready for make a model, because it reduces unwanted information. Okay, so data modeling is also another big area. So we cannot cover this one in a very short time. It is a quite complicated area. So mostly spectral information analysis is about multivariate data analysis technique. We can make regression model and also a classification model. Sometimes we can use artificial intelligence like a deep learning. Okay, so regression and classification model. There are lots of techniques. But maybe you can learn this technique in a graduate program. Okay, anyhow, let's use another let's see another example. The chemical imaging for food ingredient. Okay, this is hamburger patty, and this is chicken breast, and this is salmon fillet. We want to visualize the moisture distribution, and also we want to visualize the fat distribution of these food materials. How can we do that? Okay, so using hyperspectral imaging, we can do that like this way. So hyperspectral image is all about spectrum. So using pre-processing and the modeling techniques, we can make equation like this. Y is a target value, and X1, X2, Xm, it means spectral intensity, and V0, B1, B2, Bm is coefficient. This is a linear combination, right? Linear equation. So using this linear equation, we can predict our target values. In this case, moisture and fat. Okay, so using that spectral signal, we can predict moisture content and fat content like this one. Okay, so using the developed model, we can visualize the fat distribution and the water distribution like this one. So this is a color image. This is just a photo. So this is like our naked eyes. Can we tell what is the water content and what is fat content in here? It's not possible, right? But using hyperspectral reflectance imaging, we can visualize fat and water content like this way. Okay, this is another example of ginseng water stress visualization. First row is normal, no stress ginseng plant, and the second row is mild stress, water stress, and third one is medium water stress, and last one is severe water stress. With the naked eyes and color imaging is quite difficult to differentiate the stress plant. But using hyperspectral images, we can classify the stress plants like this way. Okay, so first one is normal one, no stress, and mild stress, medium and severe stress here. So with the naked eyes, it's very difficult, but hyperspectral imaging, we can identify the stress plants like this way. All right. I discussed about hyperspectral reflectance imaging. Now, let's think about hyperspectral fluorescence imaging. So we use fluorescence imaging for crack detection of cherry tomato. Okay, let's see this image. The ripe tomato the color is all red. The outside and inside color is all red. So if there is a crack, the inside and the outside color is same. So it is very difficult to identify the crack area using color images because all red, right? So how can we detect in this crack image in ripe tomato? So we use the fluorescence because there are fluorescence sensitive chemicals inside cherry tomato. I mean cherry tomato flesh. So like this way, there are spectral emission. It depends on chemicals. So see, the outside cherry tomato is a wax area. Wax area, there is no fluorescence. This is a blue dot line. There is no fluorescence. But crack area, this is not wax area. This is a tomato flesh area. So it's it has lots of fluorescence like this way. Okay. So using that property, we could detect crack area using fluorescence imaging like this way. Okay, so with this principle, we try to make online system to detect cherry tomato, cracks. So we design light, and the light should be high enough. So it's a UV light, and then conveyor belt. So let's see this video clip. We just put cracked cherry tomato and sound cherry tomato. So here there is a crack area clearly. Okay, so this is an example of fluorescence imaging. Okay, so another one is a rapid inspection of fake eggs. Right, there are many fake eggs in several countries. Why they make fake eggs? Because we can make fake eggs with a very cheap price. Using chemicals, we can make fake eggs. Okay, inside or outside, egg, everything we can make using chemicals. Okay, maybe 10% of regular eggs price, we can make fake eggs. All right, the real egg has fluorescence. So when we illuminate a real egg with a UV light, the fluorescence is like this way. See white egg and brown egg. Anyhow, there is a high fluorescence at the 600 nanometer. It's a red color. This is fluorescence. Okay, but fake eggs is chemical. There is no fluorescence. Okay, so using this principle, we try to make simple device to detect fake eggs like this way. So this is a handheld device. By the way, this is a real egg. This is fake egg. Can you tell which one is fake egg? Without this character, without this word, can you tell it? No, it's difficult, right? We become an expert, to make fake eggs, but should be very careful. It's a crime. Anyhow, a real egg, fake egg. So using this device, we can identify, we can detect fake eggs. Okay, I want to show you the video clip like this. So the fake eggs, no fluorescence, but the real egg is high fluorescence. So the high intensity, eggs is a real egg, but the dark one is fake eggs. Okay, we don't need hyperspectral imaging, this application, because fake egg and the real eggs, is very distinct. I mean, we can discriminate fake eggs with only 1 or 2 wavelengths. That's why we use very cheap and handheld device instead of hyperspectral imaging, hyperspectral fluorescence imaging. But the research was based on hyperspectral fluorescence imaging. Without hyperspectral fluorescence imaging, we couldn't, develop this, cheap device. All right, and lastly, I want to introduce hyperspectral Raman imaging. Okay, Raman scattering. It's a high power laser comes in, and then there is a scattering. The same wavelength comes out. That is a Rayleigh scattering, but there is also longer peaks and shorter peaks. Shorter wavelengths and the longer wavelengths peaks also comes out. That is Raman scattering. So when we look at the spectrum like this one, so high peak is Rayleigh scattering, but there is a small Raman scattering also happens. Okay, it depends on chemical structure, molecular structure. Okay, then why we need Raman? Because NIR, infrared also has chemical information. So why we need Raman signal? So because there is a reason. Okay, let's think about, let's see this figure. There is a molecular vibration like this one. It's not symmetric. It's a squid. This is anti-symmetric stretching. In this case, in this vibration, IR active. IR in infrared is very sensitive to this vibration. Okay, but Raman cannot detect this one. Okay, this rocking. This is also anti-symmetric. This is this vibration. Infrared is very sensitive here, and wagging back and forth. This is also anti-symmetric. This is IR sensitive also. Okay, but how about this? This is stretching, but symmetric, right? Symmetric stretching. In this case, infrared cannot detect this vibration, but Raman can detect this vibration. Okay, this one is sizzling, this vibration. NIR, cannot detect this vibration, but Raman detect, Raman active. This one also back and forth, but different. It's symmetric. IR inactive, but Raman active. Okay, so some chemical structure is IR active, but some some other chemical structure is Raman active. That's why we need, both technology. Sometimes Raman works, sometimes, infrared works. Okay, let me show you an example. Water consists of oxygen, hydrogen. The structure is not symmetric. Okay, in that polar structure, NIR, infrared is very sensitive to water, but Raman is not sensitive to water. Okay, so that's why we need both techniques. Okay, so we construct the Raman imaging system, for wide range of scanning. We make a special laser like this one. Laser is a line laser because we try to scan wide range of area. Okay, so the laser illuminated, and then Raman signal is detected using camera like this way. Okay, this is the Raman hyperspectral imaging system we constructed, and this is an application. Okay, wheat flour. Wheat flour is very common food materials. We make bread and the noodle with wheat flour, right? In some case, the harmful chemicals can be included in wheat flour. The benzoyl peroxide, alloxan monohydrate, L-cysteine. People put this cheap chemicals to wheat flour. I think they try to earn more money. It's bad, right? But there are some harmful chemicals inside wheat flour. So how can we detect this harmful adulteration? The color is all same. Color is just white. Okay, let's we use hyperspectral Raman imaging here. So you see this color dot is chemicals, different chemicals. So red and blue and green is different chemicals, but the gray color is just a wheat flour. Okay, so this is a video clip. We measure adulterated wheat flour, so all white color. But see, this is a resultant image. We can detect harmful chemicals using color dot like this way. Okay, it's quite fast. Right. Okay, and somebody told me, okay, your technology is good, but it's just only surface measurement. Can you detect the inside of the material? Oh man, that's important. It's a tough question, right? Yeah, but my answer is yes, we can do that, but it's quite challenging, but we can do that. So let's think about this one. The Raman imaging is like this one. There is a laser, and if we detect the same spot of laser illumination, we could get only surface information like this one. But laser is here, okay? The detector, the sensor is here. Then the light scattering is go deeper, and then get this information and comes out. And if we detect this area, then the signal contain deeper information. Okay, if the offset is bigger, increased, we could get more deeper information, much deeper information like this way. But the intensity is quite low, right? Anyhow, we could get inside property like this way. Okay, that is offset measurement. All right, this is an example. Let's measure the salmon. Okay, salmon has skin, right? Skin. Can we measure the inside salmon fillet? Okay, salmon fillet information using Raman, images. We can do that. So using offset measurement, let's see. 0 millimeter, it means there is no offset. This is only skin Raman signal. If there is offset, 2 millimeter offset, we could see some peaks. That is from salmon fillet inside. Offset is increased. We could see, maybe clear peaks, like this way. Okay. And another example, another application is pork tissue. So we hide Teflon material inside the pork tissues, 6 millimeter deep inside. Okay, here like this way. So when we use offset measurement, we could detect Teflon, hidden Teflon material like this way. With a increased offset, we could stronger information about the Teflon, but the resolution is lower than previous one. So hidden material signal and the resolution should be compromised. Okay, that is an example of offset Raman imaging. All right, conclusion. Okay, the demands for high quality safety food and agricultural material increases. So we need accurate and objective and the digital measurement technique, right? And this kind of technique will be more popular in the future. Non-destructive technology like hyperspectral imaging is still expensive. The system price is quite expensive, but my experience, this price is going down continuously. So after several years, after some time, the price become reasonable, and also the performance is good enough. Then this technology become more popular, like a color image device. So for future research, we need some challenges for spectral information. Spectral analysis. We have to develop efficient and robust analysis techniques, and the spatial information. It is imaging analysis. So in this case, we need advanced imaging analysis and pattern recognition technology, even artificial intelligence. So deep learning technology. We are also investigating deep learning technologies for hyperspectral image analysis. I think deep learning and hyperspectral image, the combination of deep learning and hyperspectral imaging is quite good, quite promising. It's still in research stage, but it's quite promising, I think. All right, thank you very much. It's all about my lecture. If you have any question, please feel free to let me know. Thank you very much.
Thank you very much, Professor Cho. Yeah, actually, I made a mistake. Yeah, when I write about the topic, it should be imaging technology instead of imaging spectroscopy. Yeah, typo, and then it's already spread out. So I just leave it. Anyway, it's very interesting, Professor Cho, that you already delivered about hyperspectral imaging, which can be used to evaluate food and agriculture products non-destructively. Some of us may not realize that we actually have used non-destructive evaluation using images, images or photos, especially during this pandemic. We do a lot with we're using a lot internet. We can or buy food online, yeah, based on color or size or dimensions of the image. And maybe some of us already use either for research or for applications about the spectroscopy using NIR or FT-NIR to predict chemical contents. And today you combine those two techniques, how to use the hyperspectral imaging for agriculture and food evaluation. It's very interesting. Okay. Anyway, there are some questions here. I will read for you. Where is it? Sorry. Okay. Okay, one of them is from Bayu Nugraha. As you showed, we could map fat distribution of meat. Can we further generate 3D geometry of that fat area?
3D is very difficult. Maybe using offset measurement, we can make depths. We can map depth information also. So maybe we cannot measure whole samples, but some depths. Maybe we can measure some certain depths. Okay, in that case, maybe we can make a 3D, mapping. It's possible, but not always possible.
Okay, because in the last in a previous meeting we have X-ray technology, and it can construct the materials. Yeah, because it's different techniques. I understand. Okay, thank you, Prof. Jo. This one is from Bayu Sedayu. Okay, from Ministry of Fishery, yeah, Fishery and Maritime. Prof. Jo, which range of spectra, either shortwave, infrared, or near infrared, etc., will be appropriate to distinguish similar species of fish caught from different regions? Maybe based on your experience.
Right. It depends on target. Mostly chemical imaging, NIR range is pretty good. NIR range means 1,000 to 1,700 nanometer. That is pretty much good. And also shortwave IR is a wider range. I mean, 1,000 to 2,500 nanometer. It is better than NIR, but it is more expensive. So in terms of accuracy, SWIR is better, but it's very expensive. Equipment is quite expensive. So sometimes NIR is enough. In case of major chemical component measurement, NIR would be enough. NIR, okay, 1,000 to 1,700 nanometer, that is enough.
Okay, so NIR is enough, yeah, for fish. Okay.
Right.
This one from EcoVD from the International BC from seed company. Is there already applied in industry like seed company about this
seed company? Yes,
yeah?
yes. Actually, we almost done the seed research. So one of seed company want to use hyperspectral technology for protein measurement, like protein and fat measurement of soybean, because now there is no online system for soybean chemical component measurement. So one of Korean company want to use hyperspectral imaging, hyperspectral NIR imaging system for protein and fat content, crude protein and crude fat content of soybean. So it is very fast. It is gravity assist sorting. So it's falling down the seed and then using, air shot. It's very fast, sorting. Now it's developing stage now.
Okay. So seeds is very applicable. Yeah, it can be applied for seeds company or seeds research. Anyone who interested in the research, maybe you can contact Prof. Joe for further information. Okay, thank you, Professor. Another questions. Can this technology detect pests in rice insects?
Yes, yes, yeah, it's possible because if the rice infected, the chemical is changed, right? So definitely the spectral signal is changed, so we can identify that defected area. Definitely can be used.
Okay, yeah, I think so. Any materials can absorb different wavelength, so it can be reflected in different
Right.
spectrum.
Yeah. In my to my experience, when plant infected, maybe a phenolic compound maybe change it. So that picks, I think, is quite important wavelengths, and sometimes chlorophyll wavebands and water wavebands maybe change it. So that also change the spectral signal. So that would be a good indication of detection.
Detection. Okay. So Dion, it is very possible to use either spectroscopy or hyperspectral imaging to detect rice infected by pests. All right, Professor, right?
Yeah, hyperspectral is better because we could detect whole area, right? So in case of spectrometer measurement, this is quite spot measurement. It's very tedious. We have to measure each spot, I mean, as many spots as possible, but hyperspectral images, it's just to scan whole area. So hyperspectral imaging would be better. Nowadays there are some portable hyperspectral imaging device also. So we just carry this image and then just capture the hyperspectral images like ordinary digital camera. So now it's very convenient. Yeah,
How much
definitely.
is this? How
Yeah,
much?
so always the price is problem. So I think it's just about 40,000 US dollars, something like that.
40,000 US dollars for
Yeah.
portable, yeah, for portable. Okay, okay, okay. There's another question. What is the level of accuracy and efficiency and the constraint on the application of imaging or hyperspectral imaging or spectroscopy in the food industry?
Yes, this is a very general question. To my experience, I mean, food ingredient, I mean, major component, the accuracy is less, the error is less than 5%. So it is quite good. It shows very good performance. I think it's ready for commercialization if the measurement is convenient enough. So the performance is very good. Spectral analysis is quite robust and proven technology. Okay, so hyperspectral imaging is also like a spectroscopic technology, but it depends on system spec, because some hyperspectral has very higher higher resolution, higher spectral resolution, but some economic system has lower resolution. So it depends on your purpose. I mean, if you need very precise measurement, you have to choose higher I mean spec system. So yeah, right.
Okay. It depends on the purpose, yeah. As you said that the choice of technology depends on the characteristics and the conditions of samples and maybe resources we have, and also the purpose. Yeah, maybe we don't need to have a higher or sophisticated technology for small or easy detection. Yeah,
That's right. That's
Prof.
right.
Okay. Okay, I have a questions. For offset measurement using Raman, yeah, will the intensity will decrease as the deeper the measurement, will the intensity decrease?
Right. That's right. It should be compromised, because light scattering, if the light illumination and the detection area, this is offset. The distance is offset. If the offset is increased, the collected signal becomes weak. Okay, if we cannot increase the offset infinity, so there should be a certain limit. It depends on target materials, so meat and some other fruit or vegetable, the scattering property will be changed. So there should be a certain limit of offset.
Okay, so it's possible, but we have a limitation, yeah, for the offset.
Right.
The
Yeah,
maximum,
agriculture. Right, agriculture sensing. There are lots of factors which influence the performance of sensing. So we have to very careful about these factors. We have to optimize this factor to get best quality, best signal. Okay.
Okay. Not yet a new questions here, so I will ask because we still have time. Is it okay, Professor?
No problem.
Okay. Oh, there's a question here. How far imaging spectroscopy or imaging or maybe spectroscopy technology and hyperspectral imaging used in South Korea?
South Korea.
Yeah.
Yes. Now, smart farming technology is very hard in South Korea. Actually, government support lots of research about smart farming technology. So one of a promising technology is spectral imaging and spectroscopic technology in smart farming technology. So we use hyperspectral imaging system for drone measurement, and also smart farm greenhouse. We try to monitor the plants, stress and nutrient deficiency of plant so rapidly. So in that case, we are using hyperspectral imaging system. So yeah, now it's very popular, and also there are several research groups in Korea. I believe we are one of the leading groups on hyperspectral and imaging analysis research.
Sorry, I'm muted. Oh, it's still muted. Sorry, Professor. I remember that last time I was in your lab, and there's your students doing the maybe he's trying to make a 3D construction of the ginseng using hyperspectral imaging. How's the result?
Oh, 3D imaging with hyperspectral imaging? No, it's not. It was not hyperspectral images. It's hyperspectral image is just a 2D measurement, but color imaging we are using. We try to make a 3D reconstruction with color images. Color images we use several camera simultaneously measurement and then make 3D images. But hyperspectral images, wow, the data is too big. I mean, so now hyperspectral images not feasible for 3D reconstruction. It's too early. I think computation time is very, very long.
Oh, okay. So the idea is there, but the facility is not
right. Maybe multispectral imaging. Maybe we can make a 3D multispectral images. But hyperspectral images still we have many obstacles to overcome.
Okay. What about the Raman? Will it distract the chemical of the products based on your experience?
Raman? No.
I mean, will it distract the compositions or?
So using Raman?
Yeah.
No, even Raman signal is high, but it doesn't distract the sample. Our Raman hyperspectral image, the power is 450 milliwatt, and it doesn't hurt. I mean, it doesn't break the samples. It's okay. It's non-destructive measurement.
Okay. Okay, it's very interesting. Is there any questions from audience? No? Okay. Okay, there's another one. Hyperspectral imaging often entail data deluge. Is it possible to compress that data to improve efficiency?
I mean, hyperspectral image is too big. Rest, it's really big. Maybe I couldn't use compressed technique, but so one let's see, one solution is in that case remote sensing. We are using drones and hyperspectral images when we measure a wide range of field. Actually the image is quite big, but still if we use external storage, it's okay. We can measure I think at least almost 30 minutes hyperspectral scanning. We can handle it. So I don't know if too big. Maybe we have to break down the data, and then if we transit the part of the data and then delete and then collect, this kind of maybe a technique may be necessary, but I think it's not a big deal. So we can maybe we can handle it, I think. Yes.
Yeah, so at the moment you can still handle the data from hyperspectral imaging. Okay.
But the one comment is if we use hyperspectral imaging for deep learning analysis, that is quite challenging. Now we have GPU based very good deep learning computer here, but still hyperspectral imaging, the size is too big. It's not good for deep learning analysis. In that case, we may need a very good deep learning computer. That is quite challenging, but we are still struggling on that. But yes,
yeah. Okay, interesting. Another question is, because of the spectroscopy, especially, it's already developed, Professor. Yeah, it's been years. Yeah, people are using that. Are there still any application for this technology that can be improved or detect using this technology, spectroscopy and hyperspectral imaging?
Uh, I think one of my interest is to make very fast hyperspectral imaging system. I mean, now the analysis tool, we already developed many good analysis tool, but the hardware is still expensive and sometimes it's slow. So I wanna in my future research, I'm very interested in developing high-speed hyperspectral imaging and with a cheap price. That is I think that is my last goal in my research.
Yeah. Okay. Yeah. There's a question, but the question is actually for me. He's asking about the equipments, yeah, either NIR or hyperspectral imaging. Are they available in Indonesia or in Gajah Mada? And I can say that it's not many in Indonesia, Professor. So maybe we FTIR, maybe we have some, yeah, but FTNIR not many. I have a very low price FIS NIR, Professor. Only the range is only from 350 to 1,000 nanometers, but it's quite good to get maybe a fluorescence or something like that. And hyperspectral imaging, I think I never seen or heard about that in Indonesia, but maybe I will ask some of our friends in other university, but not really developed, Professor. Yeah, this our problem. So, is there any questions from audience? If not, before we come to the end, you have other comments, Professor? Maybe you need to add something.
No. I appreciate your invitation. Always, I'm very happy to work with you and students in Gajah Mada University. In my lab, I have yes, 3 students from Gajah Mada University. They are working very hard and very good. I appreciate your support and collaboration. So thank you very much.
Okay. You're welcome, Professor. Yeah, we are also happy that you can accept our students to study there. Yeah, just because there's no other questions, maybe we are now coming to the end of this meeting. On behalf of the Department of Agriculture and Biosystem Engineering, would like to say thank you and give you this virtual certificate.
Oh, thank you very much.
Yeah. Okay, thank you, Professor. I believe your lecture will give new understandings and will increase our knowledge about hyperspectral imaging and spectroscopy. And we just hope that we can invite you to come again to our campus after pandemic ends.
Okay, I hope so.
Yeah. Okay, see you next time, Professor Cho. Take care.
Okay, thank you very much. Bye.
Bye.